So this thesis was done in collaboration between the Sorbonne Université in Paris under the supervision of Perzynski as a part of the Magenta project, as well with the financial support of CNPq. And part of it was done in Brazil under the supervision of Jérôme Depeyrot in the group of the complex fluids group here at UNB with financial support of CAPES. So I'd like first to give an introduction about the ferrofluids and the carbon nanodots. So the ferrofluids that we study here, they are charged iron oxide nanoparticles dispersed in an aqueous media or in an ionic liquid. So the ionic liquids that we study here are EAN and MMTFSI. So these are colloids, so they are known by their stability, and they do not separate under the application of an external magnetic field. So their most important properties for us here are their remarkable thermophoretic effect and their magnetic properties. They can be used in applications as such thermoelectricity, nanosensing, and in biomedicine. On the other hand, we have the nanocarbon dots. These nanodots, they are particles composed by carbon, and they are considered to be zero-dimensional because they are very, very small. They are well known to be dispersed in polar media, and their most important property is their bright and tunable fluorescence, as we can see here in this picture. They can also be used in energy conversion applications, as in solar energy harvesting, as well as similar applications as ferrofluids in nanosensing, photocatalysis, and biomedicine. So first, I would like to talk about the magnetic nanoparticles alone, the magnetic fluids. So our motivation here is to analyze the thermal diffusion in room temperature ionic liquids, the ethyl ammonium nitrate and MMTFSI, in order to find potential candidates for energy conversion applications. So the first step we do here is a characterization that we probe the interparticle interactions. Then we investigate the implications of the different counterions, the water content, and the application of an external magnetic field in the thermodiffusive coefficients, the Soré and the diffusion coefficient. In the next sections, you can follow which sample I'm talking about here on your right. So first, let's talk about the dispersion in ionic liquids. So we start from an acidic ferrofluid in pH around 1.5, composed by megamite nanoparticles. So this is stable, and then we need to do a surface coating in order to be able to disperse them in ethyl ammonium nitrate. So we add citric acid and create a citrate coating and regulate the ionic strength by several washings to around 10 to the minus 2.5 mole per liter. Then, with the addition of a base, we can tune which counterion we'll have in the final dispersion. Here we use sodium, rubidium, and lithium. The addition of this base sets the pH to around 7. Then we will obtain a stable ferrofluid in an aqueous media. In order to do the transfer to the EAN, we simply add a similar volume of EAN, and by freeze drying, we can remove the water. So then we'll have a dispersion in pure EAN. Here I show the ions, the cation and the anion. Then, in order to disperse them in MMTFSI, we have to perform washings until we reach the point of zero charge. And then we'll add HSMTFSI to create a surface coating of the deuterium SMTFSI. So after this step, we can add MMTFSI, and by freeze drying, we'll remove the excess content of water, obtaining a ferrofluid in pure ionic liquid MMTFSI. Here is the cation, and here is the anion. We can see that we can also obtain different amounts of water in this sample of pure EAN by mixing these two samples, since EAN and water are mixable in the whole range of fractions. These syntheses were performed previously in these two works, and their size was determined by transmission electron microscopy and magnetization, which averaged around 7.4 for the samples in EAN and water, and 9.6 in samples in MNTFSI. So let's now talk about how we can probe the interparticle interactions. So we use here SAS techniques, SACs and SUNS, performed at the LLB, in which SUNS we can also change the temperature from room temperature to around 200 degrees. So with these techniques, we can obtain experimentally the structure factor, and this structure factor can be extrapolated to the scattering vector close to 0 in order to obtain the compressibility of the system. Okay, so what we can do from this point on? So the osmotic compressibility is a function of the osmotic pressure and the volume fraction of nanoparticles. In this sense, we can use two different approaches. The first one, using the Carnahan-Starling formalism for repulsive systems, in which we will have an effective volume fraction, which is a function of the diameter of the nanoparticle and the Debye length, and we can obtain the A2 coefficient. By the virial expansion of the osmotic pressure, we can also do an approximation to this second term, in which we will obtain also the second coefficient of the virial. This coefficient, if it's positive, it represents repulsive interactions, and if it's negative, attractive interactions. So now let's take a look at the experimental data. So first, for the sample in EAN with the 3 different counterions, we can see that from the sex profiles, the sodium and the rubidium, as we increase the concentration of nanoparticles, the curve intensity reduces. As for lithium, it increases. It is translated here in the compressibility. As you can see that in both systems, we can fit the Carnahan-Starling formalism. And for lithium, we can see that it actually increases. And so for the first 2 cases, we have a positive A2, which means we have repulsive systems. And in the last case, we have a negative A2, which means that we have an attractive system. In the case of the mixtures of water and EAN, we are only doing it with the sodium counterion. As you can see here, the compressibility is now non-monotonous, and then we observing this behavior as a function of A2. We see that we have 2 regimes, in which in the extremes, we have a repulsive system with A2 being positive, and in between, we have an attractive system with A2 being negative as a function of the mass fraction of EAN in water. We also observe a wetting transition that occurs of around 21 and 41% of EAN, in which we can see here in the Eppendorfs, we have a difference in the wetting. So lastly, we're talking about MNTFSI, and then this ionic liquid, it can reach up to 200 degrees, and the sample will remain stable, as you can see from the SACs profiles. So we have a large range of temperatures in order to probe it. In the case of the compressibility, we can see that it reduces as the concentration of nanoparticles increases, which means that we have a positive A2, and therefore we have a repulsive system. So where is this repulsion or attraction is coming from? So from previous works, we can see that in MNTFSI, we have a layering of the ions, in which the nanoparticle here being positive and the MNTFSI being the negative coating, it reduces the formation of different layers in which it loses correlation as it goes further away from the particle. In the case of the EAN, we see that the difference in the sizes of the counterions affect their number also in the proximity of the particle, as well as the arrangement, in which in the case of lithium, since it has a lot of ions and it actually is really disturbing the structure, we see an attractive interaction, while in both of them, we see that the organization promotes the repulsive interactions. So now let's talk about the thermodiffusion properties. In order to probe the thermodiffusion coefficients, we use here the forced Rayleigh scattering experiment, in which we can fill a cell with the sample and put it inside the thermalized sample holder, in which the temperature can range from -40 to 200 degrees. Then, using a lamp, we will create the image of this grid by an optical system that creates dark zones and illuminated zones. By the absorption of the nanoparticles, it will create a difference in temperature between these two fringes, and then will always also create a difference in concentration, in which will induce a variation of the refractive index. This variation will, when probed by a laser, will create a diffraction pattern. This pattern can then be analyzed by a photomultiplier, and the intensity measured as a function of time. In this setup, we can then obtain the Soré coefficient and the diffusion coefficient. Okay, so in addition to all of these measurements, we can also apply an external magnetic field using permanent magnets here. So when we put this down, we can apply a field that is perpendicular or parallel to the concentration gradient. Talking about now to the Soré and diffusion coefficient, I will give a brief explanation about how it works in a molecular solvent. So since the particles move in a Brownian motion due to their thermal agitation, we see that difference in concentrations will induce a mass flux. And this is proportional to the diffusion coefficient, which is a term of the temperature and is a function of the friction and the osmotic compressibility that we've seen previously. When we apply a temperature gradient, we're going to see that the particles are moving as well as the ions and the solvent. This is called the Ludwig-Soré effect, in which the coefficient that relates the temperature gradient to the concentration gradient is the Soré coefficient. In the case of a positive Soré coefficient, we have the particles moving from the hot to the cold zones, and in opposition with an ST negative, we have the particles moving towards the hot zones. This movement of ions and charged nanoparticles will also induce an electric field. This electric field is generated due to the Seebeck effect, in which is a function of the Seebeck coefficient. These two effects, they are associated. And here we have an equation that shows that there is a relation between both of them. We see that this first contribution here is thermodynamic, which is a function of the osmotic pressure and the temperature. And this last contribution is the thermoelectric term, in which we have here the Seebeck effect at the steady state and the effective charge of the nanoparticle. Lastly, we have the single particle contribution, in which we have the Eastman entropy of transfer. So let's first see the influence of the counterions in the thermodiffusion. Say the sample that we shown before in EAN with sodium, rubidium, and lithium. First, let's take a look at the diffusion coefficient. So as we can see here, the sodium and rubidium, as a function of the volume fraction, does not really change as lithium really reduces. This can be also understood in terms of the friction if we use the experimental parameters determined early by Sachs and some measurements, and the viscosity of the solvent obtained from the literature. You can see here that in low particle concentrations, the friction follows the Batchelor development. However, in concentrations higher than 4%, we see a deviation, which increases the friction. This, we think that is due to the ionic layering around the nanoparticle. However, we don't have yet a theoretical model to describe it. Now, talking about the Soré coefficient, we can see that for either sodium, rubidium, or lithium, it is always positive, and it reduces as the temperature increases. This can be understood here by this term in the equation. However, the volume fraction of the nanoparticles show a different behavior. That is, for sodium and rubidium, it reduces as T increases, and for lithium, it increases, which is proportional to the osmotic pressure that we shown before. Now, analyzing the water content, we can see that the diffusion coefficient is reducing with the increase of EAN, and that's because EAN is close to 40% more viscous than water. So as the concentration of EAN increases, also the viscosity will increase, and therefore the diffusion coefficient will be reduced. By this equation, we can actually determine an effective viscosity as terms of the diffusion coefficient using the parameters determined previously. As you can see here, with the viscosity determined in the literature of these mixtures, the experimental values that we obtain are really close. However, we don't have it as a function of the temperature. But as you can see here, in the whole range, the viscosity is reduced as we increase the temperature, as we would expect. So now talking about the Soré coefficient, we can see that we have different behaviors here as a function of the mass fraction of EAN and the temperature. So in this first region, we can see that in low quantities of EAN, the Soré coefficient is negative and increases as a function of the temperature. However, in this lower end where EAN is more present, we see that Soré is reducing with temperature and is always positive, which is the behavior that we would expect for a pure ionic liquid and the dispersion in pure water. If you also take a look at the effect of the volume fraction, we can see that when we increase the volume fraction, ST increases, which means the system is attractive, as we've seen before in the Sachs measurements, and as well similar to what we saw in lithium. However, here, and what we observe is that ST decreases with the increase of E, which is characteristic of repulsive systems in ionic liquids. So we see that in this first region, we have this behavior close to the aqueous dispersion. And in here in this range, we have the behavior close to an ionic liquid, which can be either attractive or repulsive. So where this behavior is coming from? So in water, the charge is, the effective charge is negative as measured by electrophoretic mobility measurements. And in EAN, the effective charge is actually positive, done by thermodiffusive and thermoelectric measurements. So if you take a look here at TST over key, we can see that the system starts here in the negative state. It then reaches this plateau, and then it starts to increase. So we think here the particles are negatively charged and repulsive, in which the charge is slowly reducing to almost zero. At this point, the particles become slightly charged. However, they don't have a significant positive charge to create a repulsion between the particles. So the system here is attractive. Only here, where the charge is really high, we can also have a system that is really repulsive. Although throughout this whole range, the colloid is stable at the macroscopic level. So finally, let's talk about the effect of the magnetic field. First, I would like to show you the values for MN-TFSI in zero field. As you can see, the behavior is similar to what we observed before, as the M increases as a function of T, due to the fact that the viscosity of the solvent reduces as the temperature increases. You can also see that the difference in volume fraction shows that we have a higher friction that deviates from the bachelor development. In the case of ST decreases as the concentration of nanoparticle increases, and it decreases as the concentration increases, and It also decreases as the temperature increases, which is the behavior we observed earlier for repulsive systems. Okay, so to analyze the data as a function of the magnetic field, we use the theoretical model developed by Bakri and Salis. So this model uses the magnetic contribution of the chemical potential as using the mean field approach. So we have here the chemical potential as a function of the Langevin parameter, and then the effective Langevin parameter. And here we have it as a function of the Langevin function and the Langevin parameter. This is also a function of the polar interaction parameter, as we can see here. So in order to perform this fit, we will fit two values, the diffusion coefficient at zero field and the nanoparticles diameter. As you can see here, the field perpendicular to the concentration gradient has a term alpha, which is a function of the chemical potential, the derivative of the chemical potential as a function of phi, and it will reduce the final value of dm, and in opposition, the parallel field parallel to the concentration gradient will have an additional term beta that is due to the fact that in this system we have inhomogeneities of the concentration in the Maxwell equations. So we can see here that it actually increases the final dm. So we can see that the model actually fits really well the data, and the effect is reduced as we increase the temperature. That's because this parameter here is reduced. The same is valid for ST, in which the data is also well fitted by the model, and the effect is reduced with the temperature. In only this case, we have these two additional parameters, S1 and S2. However, they are a function of the previous mentioned values. So the conclusions of this first part regarding the interparticle interactions is that in the mean TFSI, the system is repulsive and stable in temperatures up to 200 degrees. And also it is stable under the application of a magnetic field. This stability comes from the ionic layering around the particle. In EAN, this is also valid. We have a layering. However, it can be repulsive or attractive, which depends on the nature of the counterions and the water content. Regarding the thermal diffusion properties, we can see that in all ferrofluids based in ionic liquids, we see that ST is positive and it decreases as the temperature increases. There is a systematic correlation between the Soré coefficient as a function of the concentration, as well as the osmotic compressibility as a function of the concentration of nanoparticles. The diffusion coefficient is related to the macroscopic viscosity, as well as the friction follows the Batchelor model in low concentrations below 4%, and it deviates at larger concentrations. In water in EAN mixtures with sodium counterions, we observe that the standard electrolyte behavior is it's in low concentrations of water, in which the particles are negatively charged and perform a repulsive interaction. And in the high end, with high quantities of EAN, the system is as well repulsive. However, the charge is positive. In between, the second coefficient of the binomial is non-homogeneous, and then it shows that we have an attractive system, and the charge of the nanoparticle inverses going through zero. Finally, the underfield model shows that we have an anisotropy in both DM and ST, and the model fits well in the whole range of temperatures and magnetic field. So this second part here, I would like to talk about the carbon nanodots, which we have two types here. One is green emitting, and the other one is blue emitting. So our idea here is to probe the colloidal stability as a function of the pH, since this is not very well reported in the literature. We here characterize these dispersions in acidic, neutral, and alkaline media. We estimate the surface charge and their development as a function of the pH. We also analyze the nanodots organization at the nanometric level and look for implications in the osmotic properties or into the optical properties. So let me show first the two types of NCDs that we have here. So the CD1 sample we consider here is because this synthesis is done in different amounts of nitrogen and carbon regulated by the precursor solution, which is urea and citric acid. So in low quantities of nitrogen, we see that the internal structure of the carbon dot is graphitic. And with increase of nitrogen, there is a change in the structure to become the beta C3 and 4. We'll here call it CD7. In both situations, we have oxidized nitrogen groups, carboxyl groups, and amide groups, in which their quantities might change also between these two nanoparticles. Their morphology and size is probed by transmission electron microscopy, by powder X-ray diffraction, and by atomic force microscopy. We see that they are roughly spheric particles, and their diameter is less than 4 nanometers. However, we cannot really determine the distribution of the sizes since the techniques show different ranges. Here we can see that the dispersions of these particles, which is initially a powder that is just put into water, will result in this yellowish liquid, in which at pH around 12, we see that the sample is way darker. After 2 weeks, we see that the precipitation is formed, in which is reduced as the pH increases. And at pH 12, we see that the optical properties have suffered some changes. We can see here that the supernatant of even the sample with the most amount of precipitate shows that we have an homogeneous its dispersion, and with the CDs is actually we can actually know that we have CDs in the dispersion, the fact that this fluoresces under the UV light. If we take a look at the precipitate, we see that we have different scales of aggregates, as we have here ones close to 100 and 200 micrometers. And in this smaller scale, we can see that we have up to 20 micrometers and 1 micrometer, which forms these fractal structures. So in order to understand what is playing in this stability, we did surface charge measurements, in which we did zeta potential, and we also tracked the pH of the solution after the addition of the NCDs. As you can see here, the solution pH is actually changed by the addition of the nanodots, as the CD1 sample has a more acidic character, while CD7 has a less acidic one, close to where the buffer plateau here is close to 5.5, and here is close to 4. As you can see, in all cases, the zeta potential is negative, and it's more negative for CD7. So we can also see that we have here a small displacement that does not really follow the tendency before. And we'll talk about it in the next slide. Here, we imagine that the negative charge comes from the deprotonation of the carboxyl groups. And this is what is usually reported in the literature. And here we can see that it's actually the case here. In performing potentiometric and conductometric titations, we use 2 routes, one from the acidic to alkaline one, and the other one in opposite direction from the alkaline to the acidic condition. As you can see here, both of them are, they differ from each other. And if we calculate the surface charge by the amount of mass, we can see that the curves actually changed a lot by the concentration of the treatant that was used, but as well as the pKs. You can see here that evaluating the charge roughly using the size and the density of the nanoparticles, we obtain 2.5 charges per nanometer square in the acidic to alkaline route, and 4.5 for the CD7 in the same route. However, the charge is way higher when we look at the inverse route. And we imagine that this is because of the amide hydrolysis, in which it transforms the amide groups into carboxyl groups. So in this way, we have more carboxyl groups to be deprotonated, increasing the charge, and also changes the pK. So at the nanometric scale, we can probe the supernatant. As we've seen before, at the microscopic scale, the supernatant is homogeneous. However, we have some indications that we can have aggregates there. So if we perform transmission electromicroscopy, we'll have aggregates due to the evaporation of the solvent. However, we can see that we have these higher density clusters, in which it ranges from 50 to 100 nanometers. When performing DLS measurements, we see that only by the gravitational sedimentation, we can have sizes from 400 to 100 nanometers, the hydrodynamic diameter. However, when using centrifugation process, we can actually reduce it to close to 70, but this seems to be quite the limiting factor here. So we also can see by the sex measurements that we'll have here aggregates due to the fact that in this range here of distances in the real space, we see that at the 6 nanometers to close to 30, we have an increase. And after that, we don't have extra data here to be observed. As you can see, it changes by changing the pH, the format of the curve. And for CD1, we have an exponent that is between -3 and -4, which means that we have surface fractals. However, in CD7, we have an exponent that is between -2 and 3, in which indicates mass fractals. So the structure of the factors is also altered by the type of nanoparticles. When performing time-resolved SAX measurements, we can have an idea of the sedimentation process at the nanoscale level. So as you can see here, at pH 2, the relative intensity really decreases as a function of the time. And at pH 12, this is really reduced, which means that the improvement, it shows the improvement of the colloidal stability. So finally, let's take a look at that optical absorption that I mentioned before, that changes at high pH. So we can see here that for both CD1 and CD7, this is true. And if we look at the wavelengths in which this is occurring, here we see a reduction in the absorption in the visible light, as we see an increase in the absorption in the UV. And that's why the sample looks less dark. This is related to carboxylic groups, as we've seen in the literature, and this from nitrogen groups, all again indicating the amide hydrolysis. We yet have to probe quantitatively the effect in the fluorescence. As we can see here, we observe a blue shift from the sample CD7 from green to blue. So the conclusions of the second part is that these two different nanoparticles can be partially or fully dispersed in a large range of pHs. And there is a portion of it that really easily enters in dispersion in any pH. However, it forms a precipitate in which the amount of it reduces as the pH of the system goes towards alkaline. Now, the conclusions that we have about the surface charge is that the MCDs are negative, and the charge is due to the protonation of carboxylic groups and oxidized nitrogen groups. Since at really, really low pH, we also observe a negative charge. However, this cannot be explained just by the carboxylic deprotonation. We see that the stability observed in the macroscale is correlates with the surface charge. Finally, the aggregates that we observed in nanometric level is around 70 to 400 nanometers, and they can actually remain in suspension. and their size and structure varies from the type of the nano-CD and the pH of the medium. The irreversible modifications that we see in the optical properties and in the surface charge is probably due to the high hydrolysis of the amide surface groups, as suggested by both measurements. So lastly, I want to talk about the mixture of these two nanoparticles, the carbon nanodots and the magnetic nanoparticles, to create a fluorescent magnetic liquid. So this is not really new, because there is a lot of work with these mixtures of magneto and fluorescent nanoparticles. However, in all of these cases, they are not colloidally stable. When we apply a magnetic field, we can see that we have the particles separating from the carrier fluid. So here in our system, we can have the acidic condition in which the nanoparticles have opposite signs and they will attract each other. However, if we now here citrate the sample composed of the magnetic nanoparticles, we can obtain a negative charge in neutral pH, in which both of them will have the same charge and therefore repel each other. So now let's take a look first in the acidic condition. So here we use an acidic ferrofluid with core shell nanoparticles, which they have a shell of magnetite and a core of cobalt ferrite. We use cobalt ferrite here because the magnetization is way higher, and then we can have a more significant magnetic effect. So we see that if we place the sample in a magnet, there is a phase separation, as seen before in the literature. And if we mix them, we can also redisperse momentaneously the nanoparticles. However, you can see that the sample does not fluoresce due to quenching. So now let's take a look in Sachs measurements of these mixtures. So we have here two samples, one with size around 6 nanometers and one with a size around 10 nanometers. We see that by the addition of the NCDs, the curve presents a structure factor that is attractive, and the correlation peak is around the contact distance between the nanoparticles, which is close to the size of in both cases, to the size of the nanoparticles. You can see that the signal of the NC dots is really low, so here we neglect it. We can also see by transmission electron microscopy that we have these small nanoparticles that are the NC dots decorating the bigger magnetic nanoparticles. And therefore, this effect of aggregation of the nanoparticles shields the electrostatic potential and therefore reduces the repulsion and destabilize the system. So let's try to stabilize them at the neutral pH. As you can see here, at the visible light, the addition of the CD1 or CD7 to the ferrofluid does not really change their appearance. However, in the ultraviolet light, we can see that both of them fluoresce, and the case for CD7 is way stronger. In the presence of a magnetic field, here where the samples are held by this magnet, we can see that no phase separation occurs and the sample continues to fluoresce. If we take a look at the Sachs measurements, we see that the addition of the NCDs does not really alter the profile. Only with increasing concentrations, we see a small attractive potential, which does not reduce the stability of the sample. If we perform magnetic measurements, we can see that the magnetization of the ferrofluid sample, which here is the red curve, and the sample with the addition of the NCDs, which is the blue dot, remains practically unaltered in all these kind of measurements with hysteresis loops, TONHES and ZFCFC protocols. As for magnetohyperthermia applications, we can see that the specific power absorption remains also nearly the same with the addition of the NCDs. However, the fluorescent properties are altered. As you can see here, we have a reduction of about 8 times of the intensity of the emission. This reduction of the emission is partially because the magnetic nanoparticles are absorbing the excitation radiation, but we also have a quenching effect as we can see here, by time-resolved measurements. We can then determine the contribution of the quenching, which can be static and collisional. Regarding the tunability, which is the ability of these fluorescent nanoparticles to change their emission due to the change of the excitation radiation, is preserved. So finally, our conclusions here in this third part is that in acidic condition, the mixtures are not stable, and it's probably due to particle aggregation, as we've seen in previous studies in the literature. We can obtain stable fluorescent magnetic liquids at a pH around 7, and the sample presents a long-term stability, even in the presence of an external magnetic field. We see that the magnetic particles, the magnetic properties are not really altered, and a reduction of the fluorescence is observed due to the absorption of the magnetic nanoparticles, but as well due to static and collisional quenching. The tunability, however, is largely preserved. So our future perspectives here is that since we synthesize these ferrofluids based in EM MTFSI, and they are really stable in a large range of temperatures and in magnetic field, they are really promising for thermoelectric applications. Even in the fact that when you apply the magnetic field, you can increase the Sohe coefficient and therefore increase their efficiency. So measurements in thermoelectric setups are being done currently. We also want to have a better understanding of the ions and contra-ions in the system. So since we've seen the data in EAN, which is a really good model system, in which we can probe the contra-ions and the water content, we will try to replace the SMTFSI in the surface by SMTFSO or by small charged pack chains. Regarding the nanodots, since we see that the charge was well estimated in charge per grams, however, we cannot do a proper estimation as a function of the surface charge. So we'll perform surface area measurements with BT experiments. Want also to quantitatively analyze the fluorescence, as we didn't do it, we only did it qualitatively. And we'll probe this blue shift at high pH in order to understand better the mechanism of the fluorescence of these nanodots. Finally, we'll try to evaluate the performance of these magnetic liquids to fluorescent magnetic liquids in industrial applications, as they can be used in inspection of metallic parts. And we'll also try to change the composition that we here use cobalt nanoparticles that are really dark to megamite, which is more red, and then we can probably have a better effect of the fluorescence. We also want to investigate the thermal fusion and thermal electricity of these mixed samples, since now we have different particles there, and then it can probably change their thermal diffusion properties. So finally, I'd like to thank the Phoenix Laboratory for welcoming me there and enabling me to improve my skills as a researcher. I would like to thank the Magenta project and the CNPq by the financial support. As well, I would like to thank here in Brazil the group that helped me throughout these years to be able to perform this kind of experiments, and CAPS for this financial support. We also performed a lot of SAS experiments in the LNS here in Brazil, and at Soleil and the LLB in France. And this wouldn't be possible without the help of the team of Fabrício Messina, who synthesized the nanodot samples for us. So I'd like to thank you for your attention.